It is just after midnight. A student named Vaishnavi sits in a quiet room and clicks a link to open an online computer networks lecture. If we freeze time the exact millisecond her finger taps the trackpad, we can watch a highly coordinated sequence of global engineering unfold. To understand what happens next, we have to separate two concepts that are often confused. The Internet and the World Wide Web are distinct entities. The Internet is physical hardware. It is millions of miles of fiber optic cables resting on ocean floors, deployed by massive specialized ships. It is the satellites, local routers, and switches that create a global transport system capable of moving raw data from one machine to another. The World Wide Web uses that physical infrastructure to transport a very specific type of traffic. It is a vast interconnected system of hypertext documents, pages and resources linked together, speaking a common language, floating on top of the hardware layer. The routers are the road network. The web is the postal service, delivering packages over those roads. To see how human knowledge actually moves across the globe, you have to watch both systems work together. Before Vaishnavi's browser can fetch her lecture, it needs an exact address. It takes the URL she clicked and breaks it into pieces. It identifies the scheme, usually HTTPS, to know which protocol rulebook to follow. It isolates the domain name, notes the port to find the right door, and maps the path to the lecture file. But physical routers cannot read names like campuslearn.edu. They require a numerical IP address to direct traffic. The browser queries the domain name system, or DNS. This request travels up a global hierarchy, checking local caches, root servers, and top-level domain registries, until it reaches an authoritative server. That server locates the record for the university's domain and returns the exact IP address needed to reach it. With the destination known, the laptop needs to find its immediate exit. It uses the ARP protocol to broadcast a request to the local network, searching for the MAC address, the physical hardware signature of the room's Wi-Fi router. The request passes through a local switch, operating at layer 2 of the network, which directs traffic strictly between devices inside the house. It then reaches the router at layer 3, which is equipped to read IP addresses and handle traffic bound for the outside world. The local gateway pushes the signal onto the wider internet. The request has an address, a path, and an exit. It is ready for transit. Inside the laptop silicon, the browser has assembled a formatted HTTP request. It is a highly structured pulse of data specifying exactly what resource is needed. Before sending the request, the laptop and the distant server must confirm they are both ready to communicate. They execute a TCP three-way handshake. The laptop sends a synchronized signal. The server replies to acknowledge the request and synchronize its own sequence. The laptop sends a final confirmation. If the browser sent the request now, it would travel over plain HTTP. Every piece of data, including passwords and personal details, would be visible to any router or switch that handled the packet along the way. To prevent this, the connection relies on transport layer security, the encryption layer of HTTPS. The two machines perform a mathematical key exchange, agreeing on a shared secret across the open network. They use this key to encrypt the connection, scrambling the data so only the intended recipient can read it. Without this layer of encryption, data sent across the web is completely exposed. Protected by it, modern e-commerce, private communications, and secure student logins operate safely across public infrastructure.
Traveling safely inside that encrypted channel, the HTTP request arrives at the server. It carries a specific method, in this case a GET command, asking the server to return the lecture page, along with headers that provide details about the browser and operating system making the request. If this were a static web page, the server would simply locate a pre-made file in its storage and send it back. But an online course platform is dynamic. It must check the student's enrollment, track their progress, and load the correct video file. An application server receives the request and executes a running program. It queries a back-end database, extracting specific facts: the student's enrollment status, current progress, and the lecture media. The server packages these retrieved database facts into a single HTTP response. It scamps the response with a status code, a 200 OK to indicate success, and sends the payload back down the encrypted connection to the waiting laptop. This dynamic assembly process is the core of modern web applications.
It allows a single server to generate a unique, customized experience for millions of users simultaneously. The response reaches the browser as raw code. The browser parses the HTML to construct a document object model, the structural skeleton of the page. Simultaneously, it reads the cascading style sheets to calculate the exact colors, fonts, and layouts, painting the visual skin onto that skeleton. JavaScript executes to add interactive features like video controls and comment sections. Meanwhile, the heavy video file itself streams in from a content delivery network, a geographically closer server that prevents buffering and reduces latency. The fully rendered page contains text, images, and video, but its most important elements are the hyperlinks. These embedded clickable pathways point to other resources on other servers waiting to be retrieved. Earlier protocols like Gopher and FTP could retrieve files or navigate rigid text menus, but they treated documents in isolation. The inventor of the World Wide Web, Tim Berners-Lee, designed a system where any document could link directly to any other document without requiring central permission or a fixed hierarchy. By combining a universal addressing scheme, media formatting, and clickable cross-references into a single standard, the web created an open, navigable ecosystem of information. The scale of this ecosystem requires automated software to navigate it. Search engines deploy crawlers to follow these links, mapping and indexing the public web. However, secure portals like Vaishnavi's Classroom require authentication, remaining in the unindexed layer known as the deep web. The architecture of the World Wide Web enables instant, two-way communication and global access to information. A research paper or a lecture published on one continent is instantly available on another, bypassing physical distribution limits. This open architecture comes with inherent compromises. The frictionless sharing of data applies equally to verified facts and deliberate misinformation. The open structure relies on human trust, which malicious actors exploit through phishing and deceit. Furthermore, the system assumes a level of physical infrastructure that remains absent for large portions of the global population. Back in the quiet room, time unfreezes. The student's screen flickers to life, and the lecture video begins to play seamlessly. The entire process, translating an address, locating a server across the globe, negotiating a secure connection, querying a database, and rendering thousands of lines of code into a visual interface, is complete. It happens billions of times a day, operating flawlessly in the time it takes to blink.